It is now 6:06, so I'm going to go ahead and get started on this workshop. So today I'm going to be presenting to you about linked lists, and I know some of you are here in person, watching live on Zoom, or hopefully, if you're not one of those two, you are watching this recorded on YouTube. So let's go get started. So our agenda today, we are going to go over the presenters for this presentation. We're going to talk about the objectives, and then we're going to get into our actual content, and we are going to talk about nodes, linked list nodes, the linked list class as a whole, and then we're going to talk about how you can add and delete from a linked list. All right, but before we get started on that, I just want to do a quick shameless plug for the FSE Tutoring Center's social media. This is a great way for us to reach out to students who could potentially need our services and who might not know about us otherwise. So if you're watching on YouTube, go ahead and pause it. Go ahead, drop us a follow or a friend on Instagram and Facebook. And if you are live in Zoom, I'll give you a second to do that, but then I'm going to keep moving on. All right, continuing on. So hi, my name is Roman Smith, and I am today's presenter. I am studying for my BS in computer science. I am currently a sophomore here at ASU, and my role is a special programs tutor for the Fulton Schools of Engineering Tutoring Centers. So I get to make fun workshops like these to present to all of you. All right, so let's go over our learning objectives for today. So we're going to review what a linked list node is and how it's made. We're going to review what a linked list as a whole is and how it's constructed. Then we're going to review how to add nodes to the linked list at the head, the tail, and arbitrarily in the middle of the list. And then we are going to review how to delete nodes in a linked list at the head, tail, or arbitrarily within the list. So without further ado, let's talk about nodes. So you may hear this term referred to as a node or an element. I prefer node just because that's how I learned it. But you know that those are usually the same, refer to the same idea of one element or node within the larger linked list data structure. So really what a node is it's a class in Java, and thus it is instantiated as an object. And what it does is it essentially contains two things. It contains bits of information, and it contains a reference to the next node in the linked list. So the information can be any number of variables. This is really kind of a vague term intentionally because it is completely up to you what you need or want your information to be. It could be ints, strings, booleans, other objects of other classes. You know, when you get into really big projects, you'll probably have a ton of information in nodes and linked lists. And then no matter what information you have, you always have to have a reference to the next node in the list. And note that this is for singly linked lists. If you have a doubly linked list, then you would have a reference to the next node and the previous node. But in my experience, it's more common to see a singly linked list than a doubly linked list. But just know that that's also something that can happen, in which case you'd have to have two references. Okay, so those are the two main parts of a node. And so now we need to talk about how to actually construct the node. So as with any class in Java, we need to have constructors for that class to tell the compiler how to make an object of that class. So the constructors are a little, you know, you can pick and choose what you want to use. There's not any super, hard, fast rules. but generally you're going to have some combination of an unparameterized constructor, a parameterized constructor that takes some amount of information as the parameter or parameters. And then you could also have a parameterized constructor that takes in information as well as the next node reference as parameters. So I'll show you what I mean. So up here on the top, we have the class declaration. So we just say public class node or element or whatever you want to call, one section of your linked list. And then we have our data variables. And in this example that I'm going to be showing you, I've just kept it really simple. We just have a string called name. Again, you could have any number of different strings, integers, booleans, different data types, what have you. But we don't need to worry about that right now. Then we also have the next pointer. And I say pointer here. I think I talk about this in a second. Pointers, technically we're talking about references here, object references. I might slip up and say pointer sometime because pointers are basically a really, really similar aspect of programming languages like Java, C++. They don't actually exist in Java, but their references and pointers are very similar. So in Java, we're always talking about object references, not pointers, but I might slip up and say pointer. Just know that I mean reference. So we have the next reference here, and we just say node next to say that we are always going to have a next reference in any node. All right, so on the left side here, we have our unparameterized constructor. So as you can see, just like any class, any constructor for any class, we're going to say public and then the name of the class. And we're going to set this dot name to an empty string, since we don't know yet what is going to be put into that string, right? Or the constructor is not giving us any information. And then this dot next is going to point to null or refer to null because, again, we don't have anything to work with. That's the best we can do for right now. But nonetheless, it will still create the node as an object, even if its information is kind of default. And then next we have the info parameter, and it's pretty much the exact same thing as the unparameterized constructor, except that you're passing in any as much info as you have in your node as the parameter. So in this example, we are passing in a string called name, and we're assigning this dot name equals to name. And then we're just setting the next pointer or next reference to null because we don't know what it is yet. And then down here on the bottom, we have the parameter, which accepts both information and the next object reference as parameters. And again, kind of following suit, we're setting this dot name equals to name, this dot next equals to next, name and next being the parameters that were passed in. And so now our node, we have the same object node or node object that we've created in the last two, but now we just have that name and that next node reference to fill in. All right. So a little bit of practice based on the node constructors that we just talked about. What will be the results of each of these lines? So I'm going to give you a few minutes to go over these and think about what you think is going to be the result of each of these lines. All right, hopefully you have had some time to give this practice problem a try. If you're watching this recorded on YouTube, if you need more time, you can go ahead and pause the video and take however long you need. But I'm going to keep moving now into the answers here. So let's see. There we go. All right, so for the first line here, we are saying node A equals new node, parentheses. And so this works with our parameter list or unparameterized constructor. So a new node is created. The node reference is called A, and the A contains an empty string for the name and an empty reference for, or the null reference for the next node reference. All right, so 2, we are creating a node reference called B, but we're not actually linking it to any object. There's no dynamic memory being allocated. The actual data structure of the node doesn't exist yet, just basically just something that could refer to the node. So there's no compilation error or anything. It's just we haven't really made a new node yet, just the reference. 3, so this third line here, we have C equals new node, and then in parentheses, name, in quotes. So you might think this looks good as a use of our info parameterized constructor. However, this is actually going to cause a compilation error because there's no type declaration for what C is. We always need type declarations in Java. So you would need to say node C, or else the compiler is not going to know what the heck C is. And since Java is a strongly typed language, this is necessary or else it's going to crash. All right, then number 4, we say node D equals new node, and then we have in quotes sample, comma, and then the letter A. And this makes use of our parameterized constructor with both information and a next object or next node reference. So the name is going to be sample, and the next object reference it's going to be pointing to A, which we created in that first line. All right, let's continue on here. All right, now let's talk about a linked list. So in theory, a linked list is just a collection of nodes. So each node, again, has its information and its reference to the next node. And then the linked list is just a series of nodes which point to each other sequentially. So like I said on the slide, each node points to the next node in the list. And it also contains a count, just of how many nodes there are in the list. Conceivably, you could have a linked list without the count, but it's going to be really handy to keep track of that count. So I would definitely include that in any linked list that you make. So linked lists are also going to have a head node. So this is a node reference. It's not an actual node itself. So head refers to the first node in the list. And this is because if you have the first node in the list, it's referring to the second node in the list, and the second one's referring to the third, and so on. But there's nothing to actually refer to that first node. So we need to have this head pointer or reference, sorry, that refers to that first node, so that the Java garbage collector doesn't come and just destroy it for being a loose piece of memory that's not tied down to anything. And so we're going to basically keep track of whatever node this head reference refers to in the linked list. And then we're also going to keep track of a tail node, or a tail reference. So tail is not entirely necessary, but as you're going to see in a second, it's really helpful when we're trying to do operations on the linked list. So I would recommend including and keeping track of a tail node in your linked list unless you have some reason not to. So like the head, this is just a node reference that refers to the last node in the list. And I say this isn't necessary because the last node in the list, unlike the first node, does already have something referring to it, the second to last node in the list, right? So it's not necessary. It's not going to get deleted by the garbage collector if we don't have a tail reference. But as you can see, it's going to be really useful. And another thing to note is that the tail node itself, the node that the tail reference points to, it always refers to null because it is at the end of the list. It can't be referring to any other nodes or else it wouldn't be the tail. So here on the left, we have our class declaration, public class list, and the variables it keeps track of are a node reference called head, a node reference called tail, and an integer called count. And we are just going to use an unparameterized constructor where when we instantiate an object of list type, we have the head set to null, the tail set to null, and the count starting at 0. And just a little bit of a disclaimer, this keyword is not entirely necessary in this instance because there's no parameters with the same name as the class variables, which is why we use the this in the first place. However, I think it's good just to be really clear with your, with your code to make sure that you're making sure that people understand that when you say this.head, you mean the head variable for that object, not the head variable of the class in general, and so on and so forth for tail and count. All right. So let's talking about adding a node to our list, because right now our list is just kind of a figment of our imagination. We have some object called a list that doesn't really point to anything or do anything or know anything, right? So when you're adding to a list, there are 3 possibilities. You can add a node at the beginning of the list, which is called the head. You can add a node at the end of the list or the tail of the list, or you could add a node somewhere in the middle. All right, so let's talk about adding to the head. So first of all, first thing you want to do is you want to create the new node by instantiating the node class as an object. All right, once you've done that, there's going to be 2 cases here. Either the list is empty or the list is not empty. So if the list is empty, we're going to check this by asking if the head or tail is null. Because remember, in our list unparameterized constructor, when we make the list for the first time, it's empty, right? We haven't added anything, and the head and the tail are both null. So we can check if one or two of those are null, and that's how we're going to know if the list is empty. So if this is the case, we need to assign both head and tail to the new node, since if we only have one node in our list, that is simultaneously going to be both the head and the tail of the list. All right, so case 2 is if the list is not empty. So we're going to take our new node and we are going to make the new node point to the current head node. All right, but if the current head node has something else pointing to it, like another node pointing to it, it's no longer the head, is it? So then we are going to take that head reference and make it point or refer to the new node, which now becomes the head of the list. So, and that's what we wanted to do because we're trying to add a node at the head. All right, and then as always, when you add a node to a list in any way, you're going to increase the count by 1. So let's take a look at what that looks like in code. As you can see, we have our method called add to head, and all of these adding, and we're going to get onto some deleting. These should all be methods within your linked list class. So we're making our new node. I've just called it new node. Makes sense. And we're getting in a parameter called new name. So we're going to start that node with whatever parameter we are passed in to the add to head method. So case one, we say if head is equal to null, head equals new node, tail equals new node, and then we increase the count. Okay. But case two, if the list has one or more elements, we can't just do this. So this is the else, else if head is not equal to null. The new node dot next, and remember your dot notation to access the methods of a class or from an object, our object called new node, accessing its methods, we're going to use that dot notation. Or accessing, I guess in this case it's data, it's information. So new node dot next is equal to head, right? Because if we're adding it at the head, we want it to point to what the current head is, and then we're going to reset head equal to new node, and then we're going to increase our count. All right, so we have successfully added a node to the head of the list. So let's do some practice. What would happen if we changed the original code on the left to the code on the right? So the difference here is that on the left, this is the example for case two. We say that new node.next equals to head, and then head is equal to new node. On the right, we're basically flipping the first and second lines within the else clause and saying head is equal to new node, and then new node.next is equal to head. What would be the difference if there is any? And I'll give you a minute to think about this, and then I will go over the answer. All right, hopefully you've had a second to think about this. Again, if you're watching this recorded, you can go ahead and hit pause if you want more time to think about it, but I'm going to keep moving here. All right, so you've noticed, probably, hopefully, that I've put some things in capital letters that is bolded. This is because this is really important. So in the example on the right, the chain is broken. And the most important rule in any linked list is to always preserve the integrity of the chain of nodes that make up the linked list. Because if you break that chain, then basically you've severed the linked list and it isn't working as a data structure anymore. And something in there probably doesn't have a reference, and it's probably going to be deleted by the garbage collector, and thus whatever it was pointing to, that's going to be deleted, and it's going to be a huge chain reaction, no pun intended, although It makes sense because that's what it is. It's a chain. So this is very bad. We want to avoid this as a priority to literally everything else. So, and this happens because if we move the head to the new node first, then nothing will be referring to the old head node, right? Because the head doesn't have anything referring to it. If we all of a sudden switch that head reference to a different node, then that node lost all of its connection to any kind of reference. So it's kind of cast off into the oblivion of computer memory, and it's going to be destroyed by the Java's garbage collector. And since it used to be the head node, that's not good because then the rest of the linked list is going to disappear as well. So we always, and also after that happened, saying new node.next equals head would make the new node point to itself because we previously set the head equal to the new node. So now new node and head basically mean the exact same thing. And that's kind of pointless to have just one node looping to itself while we destroy the rest of the linked list. Not at all what we want to happen. So always do what we do on the left. Make sure that everything always has some reference to it. Never leave anything dangling out in the open. Make the new node point to the current head node so that it has a reference, so that you can move the head reference away from the previous head into the new head. All right, let's talk about adding to the tail. So again, pretty similar to the add to head, we're going to make a new node, and we're going to check if the list is empty. If head or tail is null, then we are going to assign both head and tail to the new node, just like we did for the head node, remember? Because if it's empty, adding to head and adding to tail is doing the exact same thing. It's just populating the linked list with its only node. But then case 2, if the list isn't empty, we're going to do something a little bit different, kind of the same idea. We are going to make the current tail node point to the new node. But again, if the tail node's pointing to something, it's no longer the tail, right? There's something after it. So then we're going to make the tail reference point to the new node, which is now the tail. And then, of course, increase our count by 1. All right, it's pretty straightforward. So now we're going to talk about adding it somewhere arbitrarily in the middle of the list, maybe in the middle, maybe at the head, maybe at the tail, we don't know. And there's a bunch of different ways to do this depending on what kind of information your node has, or what information your nodes possess. But for right now, I'm going to do this by index. So this is a linked list, not an array, right? So there's no kind of built-in indexing like there is for an array. We can't just say, oh, the 7th item in the linked list, that's the one that I want to add after or before. We have to actually kind of count our way, crawl over this linked list and count our way to that spot. So this requires an index that you want to add at to be passed as a parameter. And we have to check if that index is valid. If not, we're going to want to print an error message. And if the index that whatever is calling this function wants to add to is 0, well, that's just the beginning of the list. So then we're just going to call add at head, and it's going to do it for us. So you can see my checking to see if the index is greater than the count, because if it's less than the count, checking to make sure it's less than the count but greater than 0, because otherwise we're going to have like a bounds error. We're talking about an index that isn't within the range of numbers of nodes in our linked list. So then if we pass that, then we are going to check if it's equal to 0. If so, we're going to just call add to head and pass the new name node. Otherwise, we're going to traverse the array to find the index. So we're going to make a new node, and we're going to make two node references, not new nodes, node references. One, you can kind of call them what you want. There isn't an official name that you have to call them. Generally, one should be like temp or current or something like that, and one should be previous. And that's what I'm going to use in this example. And the point of doing this is so that we can crawl these references along our linked list until we find the location where we want to add the new node. So we're going to use a loop to do this. And one reference, the one called previous, is always going to stay one node behind the other reference, which makes sense. So we can keep track of what the previous node is. So we're going to let the new node point to the node currently at the desired index. This is once we found this, the index that we want to insert it at. We're going to make the new node point to whatever node is currently at that index, right? We're going to say, and move over, we're taking your spot here, push everything to the right or to the left, depending on how you're imagining this. And saying, you know, okay, this is my index now. I'm going to point to you. And then we're going to let the node at previous refer to this new node. Because before, the node at previous was referring to the node that's currently at the desired index. So we're just going to wedge our new node in between those two other nodes and, you know, preserve our links through the next node references. So this is what that looks like. So we are going to make a new node. We are going to make the temp, set it equal to head, set previous equal to head, and then we're going to say for integer I equals 0, I is less than the index that we want to find, right? And then we're going to increment I until we get to that index. And we're just going to set previous equal to temp. So now they're the same, but then we're going to say temp is equal to temp.next. So if you're imagining this, we're kind of advancing temp and previous up the linked list until we stop at the index. So now that we found the index, we say new node.next equals temp, previous.next equals new node. We've preserved the integrity of the list and successfully inserted the node at the new node at the desired index. So we can just increase the count and we're finished. All right, let's talk about deleting from the list. So there are three possibilities, just like there were for adding to the list. We can delete a node at the beginning or the head. We can delete a node at the end or the tail, or we can delete a node somewhere in the middle. So let's talk about deleting from the head. So we are going okay, let me backtrack. To delete a node from the head, we are going to set the head reference to the next node, the node that the node at head points to. That's kind of confusing the way I wrote that. I apologize. And that's all we have to do. Why? Because the current head, the head reference was the only thing pointing to the previous head node, right? That's why we have a head reference, is because otherwise there's nothing referring to it and the garbage collector is going to come and destroy it. So that's why we have the head pointer in the first place. So if we just move the head pointer to whatever that node is referencing, just move it one spot down the linked list, then all of a sudden the previous node head is floating off into nothing. It's going to get destroyed. So that's kind of a handy use of the Java garbage collector. You can't necessarily do this in other languages like C++, where you have to delete your own memory. But we don't need to worry about that right now because this presentation is about Java. And then once we've done that, we decrease the count. So this text-heavy slide might be a little confusing. It's going to be a lot less confusing when you look at this. So deleting head, we are going to set the head pointer to head.next. So the head pointer just moves over one spot in the array. Or sorry, not the array, the linked list. So now the previous head, it's gone. The garbage collector came and collected it. So now our new head is the one that we just made the head reference refer to. And we're all fine and dandy. So then we're just going to check to see if the count is not equal to 0. So if there was anything, in the list to begin with, or if, there is something left after we've deleted that head. Maybe the head was the only thing in the list. Who knows? If the count is, greater than 0, still we're going to take the count down to 0, or take the count down one count minus, so that because we just deleted a node. All right, let's talk about deleting from the tail. So, like deleting from the head, we need to move the tail reference to the previous node, right? Because if we move the head reference to the next node and let the head reference, let the previous head node just get deleted on its own, well, wouldn't it make sense to just move the tail to the previous node to the tail and just let the tail be deleted? And yes, that's what we're going to do. However, we don't know what that previous node is. Because all of our nodes point to next, they all know what is next in the list, but none of them know what comes just before them in the list. So we have to find this kind of manually. And we're going to do a similar thing that we did to find the index in that adding method, where we're going to take our temp node. We just need one right now. We don't need the previous. And we're going to set it equal to head, and we're going to use a while loop to advance it until temp.next is equal to the tail. And that's how we're going to know that temp is now the node that's previous to the tail. Or the second to last node is another way to think about it. So we're going to reassign the tail reference to the node that temp is referring to. And then we're just going to set tail.next equal to null, right? Because we've moved the tail reference. We're going to set tail.next equal to null. Now the previous tail has nothing pointing to it, and the garbage collector is going to come destroy it. So this is what that looks like. We got our public void deleted tail. We create a new node reference and called temp, assign it to head, so it's pointing to that same node at the start of the list. And we're going to say while temp.next is not the tail node, right? Because if it were the tail node, we'd know that temp is the node before that, because that's what it's referring to as the next node. So we're just going to say temp equals temp.next to advance that temp one place down the list. So once we found this, once the loop exits, we know that temp is the previous node to tail, right? So then we can just assign tail to temp to make temp the new tail, right? And then since temp is pointing to tail, it still has tail still has a reference, so it's not deleted quite yet. We have to set tail.next or temp.next, either way, equal to null. And then we'll completely sever that node from our linked list, and it will just be deleted. And then again, if the count is greater than 0, take the count down. All right, so the last thing we're going to talk about is deleting by data. So we could also delete by index, and I'll talk about that in just a second. I just wanted to show you a different type of way that we can add or delete something arbitrarily in a list. So the value of a variable passed is passed as a parameter, and here it's going to be a string, right? Because that's the data type, basically, that our nodes possess. It's just a string called name. So we're going to pass a string in that we want to basically say that we want to delete the node that possesses that name. All right. So we're going to use a while loop, again, to traverse the list using the temp and previous node references that we talked about before. Basically, just using these until we find the node that contains that piece of data, whatever that name of that string is. That's where we're going to stop because we found the thing we want to delete. Or if the we run off the end of the list, if temp is null, then we know that the target node the name that we want to delete isn't even in the list at all, and we've made some kind of mistake, or we're trying to delete something that isn't there, and so we need to throw an error message. So let the previous node point to temp.next. Once we found, assuming that we found the node with the name that we want to delete, we let the previous node point to temp, not to the temp node, to the temp.next node. So we're kind of from previous bypassing around the temp node to the temp.next node. So this way, the target node, which is on temp, that's what temp is right now, the only thing referring to it is the target node. So once we reassign that target node, or sorry, let me backtrack. Right now, the target node, or the temp node, the only thing referring to that is the previous node, right? So if we take the previous node the reference to the next from previous, and we change that to the one after the target node, then the target node doesn't have anything pointing to it anymore, and it's just going to float off into space and be collected as garbage. So hopefully this will make a little more sense. This is definitely the most complicated method we've talked about, but it's not too bad, I don't think. So first, we're just going to check to see if the name we want to delete is at head. So we say if head.name.equals toDelete, with toDelete being the string that we pass into our method. We're just going to call delete at head because that's where it is, and we don't have to worry about anything more than that. Similarly, if the tail name, the name of the tail, it matches the string that we want to delete, then we just delete a tail. All right. Then case 3 is if that piece of information wasn't at the head or the tail, we need to actually find it somewhere in the middle of our list. So we assign make the temp in the previous node references and assign them both to head. And then we're going to say, okay, while temp does not equal null, right? While it still points to something actually in our linked list, and not temp.name.equals toDelete. So while we haven't yet found that node that we want to delete, basically these are the conditions. Either we found the thing we want to delete, or we've run off the end of the list. And if we haven't done either of those things, then we're going to keep advancing our temp and previous pointers or references. Kind of the same idea to what we were talking about before, just crawling over the list. So once we have exited this loop, right, either the temp is going to be null, or the temp is going to be the node that we want to delete. So we're going to check, okay, if the temp is null, then we're going to throw our error saying, error, that name doesn't exist in the list. I couldn't delete anything because you gave me a name that doesn't exist. Else, if this is not the case, then we know that we successfully found that node that we want to delete. So then we're going to do previous, take the node previous to the one we want to delete, say previous.next equals temp.next. So then it bypasses the current temp node. Temp doesn't have anything pointing to it except the temp reference, but that will get deleted when this method finishes because it's a local variable. So as soon as this method finishes, the temp node is going to get deleted by the garbage collector, and then we can take our count down. All right. So I just want to quickly touch on some other methods. There are many possible linked list methods that you could have. You can kind of customize linked lists a lot. You can have doubly linked lists. You can have circular linked lists. Those are fun. And you can do a bunch of different crazy stuff with linked lists. Way too many that I have time to talk about here. So there's other ways to add. You can add before or after a specific node or a node with a specific value, a variable, like we kind of talked about. You can delete by index, which is similar to adding by index. And you can find and return certain nodes or values of variables without deleting those. So just know that this isn't a comprehensive list of everything that you need to know or could want to know about linked lists. It's just kind of a basic review of how to add and delete from one. All right, so what we just reviewed is nodes, linked lists, adding nodes to a linked list at the head, the tail, and arbitrarily. In this example, we did it by index. And then deleting nodes from a linked list at head, tail, or arbitrarily. In this example, we did it by value. That is all I have for you today. Hopefully, whether you're here live or watching this recorded, this video was of help to you. Hopefully it cleared some things up about linked lists or just reinforced what you already knew. Again, come check out all that the Fulton Schools of Engineering Tutoring Center has to offer. And I hope you all have a fantastic day. Thank you for coming.